Imagine a piece of fabric, an infinite elastic sheet representing space itself. When we apply a linear transformation, a matrix, we are essentially stretching, squishing, and rotating this fabric. To the naked eye, this looks like chaos. Every point moves to a new location. Every direction changes. If you look at this red arrow, it gets knocked off its original path. It rotates. And this one? It swings to the left. It seems like the transformation changes the orientation of everything. But hidden inside this chaos, there is a spine, a secret structure that resists the rotation. Watch closely, I'm going to apply the exact same distortion again. See that? The grid warps, the red arrows spin, but the orange arrow, it stays on its line. It's stretched, yes, but it didn't turn. It is the eigenvector. In German, eigen means its own. This direction belongs to the matrix. It is the true physical axis of the transformation. Every other vector is just a tourist being pushed around. The eigenvector is the local guide. It knows the terrain. So, how do we write this mathematically? It's surprisingly simple. Usually when a matrix A acts on a vector V, it changes direction. We write that as A times V. But for our special vector, the result is just a scaled version of itself. This lambda symbol, that's just a number. It's the scaling factor. If lambda is 2, the vector doubles in length. If it's 0.5, it shrinks. If it's negative, it flips. This is the eigenvalue. It tells us how much the space stretches along that spine. Wait, why do we care? Why does a data scientist need to find this hidden axis? Because usually data doesn't come in a nice grid. It comes as a messy cloud. Imagine this is a data set of two variables, maybe square footage versus house price. The data has a shape, it's not a circle, it's an ellipse. If we just look at the x-axis or y-axis, we miss the relationship. We are looking at the data from the wrong angle. We want to find the natural axis of this data, the directions where the data varies the most. And there it is, the long axis of the ellipse. This line? This is the eigenvector of the covariance matrix. It points in the direction of maximum information. It's the spine of the dataset. There's a second eigenvector too, perpendicular to the first. This one represents the noise or the lesser details. Here's the magic trick. We can use these vectors to change basis. We rotate our entire perspective so that the eigenvectors become the new x and y axes. Look at that. The data is now perfectly aligned, the correlation is gone, we have decorrelated the data. This is principal component analysis, or PCA. If we want to compress the data, we can simply delete the small red axis. We reduced the dimensions from 2D to 1D, but we kept almost all the important information. Eigenvectors aren't just abstract arrows, they are the skeleton keys that unlock the true geometry of the data. Next time we climb the mountain, we take these concepts into the landscape of calculus to find the lowest valley.